The second section, we are going to learn about breadth first search or BFS. So we are going to learn about the concept of BFS and what is the BFS algorithm and what is the property of BFS. Okay, we have a different way to discover the path. So there's another concept about the path and graph. We call it path graph. So the path graph or the linear graph is path with at least two vertices is connected and has two terminal vertices. So the vertices that have 1 degree. So we call it the terminal vertices. It is the vertices that have degree 1. So for example, if you go by bus, what is the job? So the final destination or the final bus stop. Okay? So that will be the terminal vertices. That's why we call it bus terminal. So this is the vertices that have degree 1. So while others, if any, have degree 2 or maybe more. So this is what we call as the path graph. Okay? We have at least two terminal. Okay, this is the first terminal and this is the second terminal. So we can also have a path for the subgraph. So paths are often important in their roles as subgraph of other graph. So this is a subgraph of graph. And there can be another kind of subgraph. So paths are often important in their role as a subgraph of other graphs, in which case they are called paths in that graph. There might be another concept, we call it bipartite graph. Bipartite graph. Bipartite graph, or usually we call it pie graph. Pie graph means a graph whose vertices can be divided into two disjoint and independent sets, U and V. So U, it is a collection of vertices. And then V is a collection of another vertices. And we want to connect from U to V in this vertices. So we want to connect this vertex and this vertex. We want to connect this vertex and this vertex. We want to connect this vertex and this vertex. So every edge connect a vertex in U to one in V. So at least there's one connection between each of the vertex in U and each of the vertex in V. So bipartite graph or bigraph are used extensively in online space. So if you are doing with the social media, like the Instagram or maybe the advertising, e-commerce, usually we use this thing. So let's say you are in this node. So I want to know whether you are connected to or you are connected to another community and etc. So we can have the pie graph, bipartite graph as G. We have U, comma V, comma E. So it means we have U, which is a set of vertices. V, it is a set of another vertices. And E, it is a set of connected V, okay, or connected vertices between U and V. So where U and V are the set of nodes and P is the set of edges on the graph. So we can also look at the bipartite graph as a kind of users and items. For example, this user buy this item and the users buy this item 5 pieces. This user buy this item 1 pieces. Or maybe this user interest on this item and click that item 5 times. These users have interest on this item and click this item for 1 time, and also and etc. So we can also use this kind of things as the pie graph. And this thing we can make a kind of matrix. So the users has interest on item 1 for 5 times. The users 1 has interest on the item 2 for 1 time, and so on. So we can make this kind of graph. There's another kind of graph, we call it graph structure stack. It means we want to use stack for creating a graph. So graph structure stack or GSS is a directed cyclic graph. If you still remember directed graph. What is directed graph? It is a graph with direction. Acyclic. What is acyclic? It is no cycle. Okay. Acyclic means no cycle. So where its directed path represent a stack. Okay. This one is a stack. This one is a stack. This one is a stack. So you can see if we look at this one, there will be 4 stacks. 7, 3, 1, 0. So this is one stack. And 7, 4, 1, 0. 7, 4, 1, 0. This is another stack. And then 7, 5, 2, 0. This is another stack. And 8, 6, 2, 0. This is another stack. Okay. The other kind of application, if you are doing with the large language model, or if you are doing with the NLP, so we use this one to generate the grammar. So if you have a sentence, then you will need some kind of structure, whether the structure will be a noun or verb. And then if it is a noun, then there will be an adjective, or it is a collection of another noun phrase. For example, adjective and singular noun. This little boy or the little boy. And then we have the verb and adverb. Run quickly. So we can also create this one as a graph. So we can also use stack for the graph traversing. Traverse means travel. So in the previous section, we learned the graph traversing using BFS. We can also use the same idea for the traversing using stack. How? So let's assume we start from S. Then visit the first neighbor S. So let's say the first neighbor is T. So we put T. Then visit the neighbors of that neighbors. Let's say P. Every time consider the neighbors of the last vertex visited. So if we have the V, and then we want to visit U, we want to visit W, and then we at the end we visit X. So every vertex can be put into the stack. and then we pull out from the stack, and then we make the root. What is the root from S? And we can make a spanning tree. Okay. So this is using stack. And also we can make the graph traversing with queue. So if you do with queue, okay, so we learn the BFS, we will visit the neighbors of S. Okay, so we will visit the neighbor of S. Let's say we have T is the neighbor, and then let's say we have U as the neighbor. So T will go first in the queue, and then it will goes out early. So we have the concept of T4. U will be the next, and then V will be the next, W will be the next, and the last will be X. So we can just have a spanning tree with the T, U, V, W, and X. So we use the graph traversing with Q. So Q is the first in, first out concept. Okay, we learn this one before the mid-descent. Now, yeah, I would like to focus on the breadth first search. So it is a general technique for traversing a graph, and BFS traversal of a graph visit all the vertices and edges of G and determines whether G is connected. So again, we need to check whether it is connected and computes the connected components of G and compute the spanning forest of G. So the idea for the DFS and BFS, they are the same. We need to create the spanning, or yeah, if you want to make it more general, we can say we want to make a spanning forest. So if it is a spanning forest, there might be some non-connected component. Non-connected component. If it is the spanning forest. BFS will run On plus M. So we have N vertices and we have M edges. So BFS can be further extended to solve other graph problems. For example, yeah, you can find and report a path with the minimum number of edges between two given vertices. And we can find a simple cycle if there is one. Now let's look at the algorithm of BFS. The algorithm still use the same mechanism, setting and getting. So we want to set the labels and we want to get the labels from both vertices and edges. Now we have the PFSG and we have the PFSG, S. The PFSG means we are going to label all the edges and the partition of the vertices of G. So let U be all the vertices. So set the label U as unexplored. Let E all the edges on G. So set all E as unexplored. And then for every V in the vertices, if the label is unexplored, do this one. So we will do the BFS G, S. Now let's look the overview. We have the BFS G, S and L0. L0, L. L indicates the level. We have another concept about level. So it is an empty sequence and L0 at last S. So we put the vertex into L0 and then set the label as preceded. We start I from 0 and then check. If Li is not empty, so Li, because I is 0, so L0 is not empty. If it is not empty, then do this one. So what is inside? Li plus 1. So we will add the I with 1 and it becomes L1. So L1 will be a new empty sequence. For all V in the Li elements from this one, we want to check all the elements from Li and it becomes the V. So if there are E, E means the edge from V. So you have V, we have the incident edge of V. Okay, so this is E, the incident edges. If the label is unexplored, check the opposite of V. So let's check the opposite of V, which is W. So the idea is the same with BFS. But now, if the label is unexplored, so set the label as discovery. So we set this one as discovery and then set the label W as visited. And then Li plus 1 at plus W. So we put W in the L1. What about if not? If not, we will set the label as cross. Okay, so what is cross? We will check. After all finish, we will add I with 1. So if I plus by 1, then it becomes L2. So L will be added until empty. Now we can see this is the Python code for the BFS. So we have a level. The level is started with only one node, which is S. And then when the length of the level is higher than 0, so the next level will be started with empty list. And then check where the U is in the level. So we want to check for the level because we have 1. So we will start. Now we will check the incident edges of U, the incident edges of this vertex. And then check what is the opposite of U. If V is not in the discover, then let's put E into discover. And then the next level will append the V. And let be the level equals to the next level. So let's see one by one how we can perform this one. Again, the blue color indicates the unexplored vertex. The yellow color means the visited vertex. And then the solid line without arrow, it is unexplored vertex. Oh, sorry, unexplored edge. And then the solid line with arrow, it is discovery edge. And the dashed line, it is cross edge. So what does it mean by cross edge? Let's see. Let's assume we start from A. Now, the L0 is A. Because everything starts from unexplored. Okay. So we start from A, which is unexplored, and then we go here. This is the L0. And then we start from I plus 1, which is L1. And then in the L1, we check what is the incident of A. The incident of A is B. Then the A and B, now it becomes DE. So it is discovered. And then A is already visited at the first time, and then because this is discovery, B now becomes visited. So this is based on the step by step of this algorithm. Now let's continue. If we have the B, we have at the first time is A is visited and B is visited, and then we are now in the L1. In the L1, at the algorithm, we want to check the incident edges of A. Okay, this is the incident edges of A. AB, at originally, it is unexplored. So we explore to B. And then we go back to here and then check A to C. A to C is originally unexplored. Then we explore to C. Now AC becomes discovery X, and then C becomes visited for that. So after this one, if you check this one, now we are in the L1, in the L1. So L1 still has the Li means the L0 still has the element. If you check the element, it is still the A, and then we want to check the incident edges. The incident edges, it was AB, AC, and now we want to explore AD. And then we'll check. Is AD unexplored? Yes, previously it is unexplored. And we check what is the opposite of A. The opposite of A is D. So check whether the label is unexplored. Originally, D is unexplored. So we set the label E as discovery, and we set the label W as discovery. So we set this label D as visited. And then Li plus 1 at plus W. So in the L1, we put D. So now in L1, we have B and C and D. After this, let's continue. Now, is all edges already finished? Yes, because all edges already finished. Now, let's go to this Li. Li means it is L0 at the first time. L0 elements, it is only A. Then we finish. Because we finish, now I will be added by 1. I added by 1, now I becomes 1. So Li plus 1. Then we start L2, it will be empty sequence. Now we will check for element Li, which is L1. So we have B, C, and D. Start from B. So for all E in the incident edge of V. So for P, let's check what is the incident edges. So we have these incident edges. Like the label A, okay, let's check what is the label E. So B to C. B to C, actually originally it is, because there is no label here, it is unexplored. Then check what is the opposite of B. The opposite of B is C. Now we will check what is the label of C. Is the label of C is unexplored? The label of C already visited. Because the label of C is already visited, so we cannot do this one. We will do set the label as cross. Okay, cross. What is cross? We call this is cross edge. If it is cross edge, it means this is an edge in the same level. It is the edge in the same level, or it is the edge in the L1. Because it is in the same level, so yeah, we put this one as CE, and it is not the discovery edge. And then we go to explore different incident. So we check the PE. PE is another incident edge of B, and then check whether the label E is unexplored. Yes, it is unexplored. Check the opposite of B through this edge. Okay, the opposite is E. So let's get the label of E. Is E is unexplored? Yeah, this is unexplored previously. And then we have this condition. Set the label E as discovery. So set the label E. This is B to E as discovery. And then set the label W as visited. Set the label E is one as visited. And then Li plus 1. Now we have L because I previously is 1. Now it becomes L2. So L2, put the E into the L2. Now we have L2 with 1 node. And after this, we need to check another possibility of B. Is there any incident edge of B? No. Yes. Then we will explore another possibility from the next node in the same level. So we will check for another V in the Li. So I still equals to 1. Then we want to check what is the other V. So we want to check C. In C, we want to check the incident edges. So the incident edge of C. The incident edge is this one. And then check whether the label E is unexplored. C to D is unexplored. C to D is unexplored. So we check the opposite of C. The opposite of C is D. The label of D is unexplored. Is it D? Originally, the D already visited. So because D already visited, then we go here. Set the label E, so CD as crosscuts. Then we continue to find the incident edge from C. The incident edge from C, we can go from C to F. And then check the label E is unexplored, yes. And then find the opposite of C. The opposite of C through this edge is F. So F is unexplored, yes, F is unexplored. Then put the label CF as discovery, and then set the label W as visited. So Li plus 1, so L2. Now we have another node, that is F. We will check another possibility of the vertex V, because it is not finished from this one. And then check what is the incident edge. The incident edge from D is this one, D to F. So the label E is unexplored, DF is unexplored, yeah, because we have no DF. And then check the opposite of D. So the opposite of D is F. What about F? F is unexplored, so F already visited. Then, because F already visited, we put the label D to F as process. Maybe I can show it this one. Yeah, this one. DF is process. Okay. So using the BFS, it is also another connected component. Okay. If you look at this one, then it is a spanning tree. Okay. We have A, B, C, D, and then it goes to E, and then it goes to F. So this is the spanning tree. GS is a connected component S. So the property of BFS, if we have G comma S, it means we visit all vertices and edges of GS. And the other property means when the discovery edge is labeled by BFS G comma S, it will form a spanning tree. Okay. So as I mentioned to you, this is the spanning tree. This is the spanning tree. And the property tree means its vertex V in Li. Okay, so this is the vertex in L0. This is the vertex in L1. And this is the vertex in L2. So the path of TS from S to V has I edges. The path from TS, so the path from S here has I edges. So we have 1, 1, 1. So this is 1. If it is 2, so from the S from A, it has 1. From A to F, it has 1, 2. So that's the meaning by this 2 and this 1. Every path from S to V in GS has at least I edges. So starting, setting and getting. So this is the same idea with the DFS. When we want to set and get of vertex and edge, it is only O1. And its vertex is labeled twice. We have unexplored and visited. Its S is labeled twice, whether it is unexplored or discovery or process. Its vertex is inserted once into a sequence Li. And the incident edges is called once for its vertex. So that's why we can have the BFS. It will run On plus M when the graph is represented by adjacency list. And we still use these properties of the graph. So the BFS can be used in many ways. Okay, for example, using the method that you already learned, we can specialize the BFS traversal of a graph to solve the following problem in On plus M. So you can compute the connected component of G. You can compute the spanning forest. You can find a simple cycle. You can report whether G is forest. And then you can find the path. So if you give two vertices, find a path in G between them with the minimum number of edges, or report that no such path exists. So usually we can also use the BFS as the short path problem. So here are some of the application. If you want to find the spanning forest, connected components, if you want to find the paths, you want to find the cycles, you can use either DFS or a BFS. If you are doing the shortest path problem, maybe BFS is the. If you are finding the bi-connected components, so maybe the DFS is better. So this is the result of BFS. So we have A, B, C, and E, and D, and F. So this is the spanning tree of DFS, and this is the spanning tree of BFS. So what is the difference? We call it depth. So we explore from this node to this node to this node to this node, and then go back to this node and go back like this one. But for the BFS, we explore 1, 2, 3, and then go deeper for from every of them. The way to discover the spanning tree is different. So the spanning tree will also be different. And in the DFS and BFS, you learn there are two things. Okay? If it is back edge, okay, in the DFS, it means W is an ancestor of P in the tree of discovery edges. So if it is back edge, like this one, back edge, this is the ancestor. Ancestor means the parent or grandparent. If it is cross edge, so this is the cross edge. So it means W is in the same level as V, or sometimes it can be also in the next level. Okay, so B and C, they are in the same level. C and D, they are in the same level. C and E, it is in the different level, but it also can be cross edge because E has been visited. D and E, it is also cross edge because F has been visited. Okay. Okay, so that's all. I think I finished everything. Any questions? If no question, then